So this question is about the problem of exploration in bandit problems. And we're going to imagine that we've got two arms of a bandit, and what we'd like to do is learn to, well, we want to gather as much reward as we can. And our experience so far is that we've pulled this arm a total of 5 times. 3 of them were payoffs, we won, and 2 of them we didn't, we lost. We pulled this arm 751 times, no, sorry, 1,000 times, and 751 of those it paid off, and 249 of them it didn't. So in terms of the raw scores, this one pays off about 67% of the time, and this one pays off about 75% of the time. So in some sense, this arm, at least at the moment, appears to be better. But the fact of the matter is that we just haven't really pulled this one very much, and it might be better and it might be worse. So if we commit all our resources to playing this arm B instead of arm A, we very well could end up playing something that's quite a bit suboptimal. Now, in the Bayesian setting, the way that we actually model this is to use a beta distribution, which is a posterior over the payoff probability. And it's very easy to update this posterior as new data comes in because it has 2 parameters, this distribution, the number of wins and the number of losses. So it's quite simple. We pull the arm and we can update either the win or the loss column. Now, there's tools for actually plotting what this curve looks like. So here, for example, is the beta distribution that comes from 3 wins and 2 losses. And you can see it's peaked around 2/3, but it's actually, a fairly fat curve. And in fact, there's some probability that the actual payoff is 0.99, and there's some probability that the actual payoff is 0.1, but it falls off, and it's highest when it's closest to 2/3. So let's compare this to the curve that we get for 751 wins and 249 losses. So here we have a distribution that, of course, is peaked around 75.1%, but it's much more peaked. In fact, the probability that the real payoff is something like 0.9 is completely negligible. The probability that it's 0.6 or less is negligible. It's very, very likely to be between 0.7 and 0.8. In fact, it's most likely to be about 3/4. So one strategy for deciding which arm to pull next that doesn't get stuck in the problem of just always pulling the arm that seems to be the best and not exploring enough is the notion of Thompson sampling. In Thompson sampling, what you do is you look at the posterior that you get from the 2 different distributions, and you draw samples from them, where the probability of any given sample is proportional to the probability in the posterior, and then you choose the arm that actually has the highest sample. For one round, update your posteriors, and then go back and start over again. So the question is, in this example here, what's the probability that Thompson sampling will choose arm A? It's maybe more likely to choose arm B because it has a higher probability, but there's some significant probability that, that arm A will get chosen. So what is that probability? And just to give you a hint, it's not obvious to me how to calculate that. So you can try calculating it by looking up information about the way that this distribution works. Or maybe you could actually do some samples yourself and run some simulations and see. But you're going to need to be able to compute it to within at least, say, two decimal points of accuracy.